You think you know what a magnet is, right? It's that thing holding a grocery list to your fridge. It's one of the fundamental forces of nature. But what if I told you that in a very, very real way, the magnetic force doesn't actually exist?
Now that is a bold claim. This comes directly from our source material, and it says that from the point of view of any single electric charge, there's no such thing as a magnetic field. At all. There are only electric fields.
Okay, so if that's true, then what in the world is this force we've been calling magnetism? I mean, what is literally happening when a magnet snaps onto your refrigerator door? It sure feels real, and that's the puzzle we're going to solve today.
To really get to the bottom of this mystery, we're going to use one of physics' most powerful tools, a good old-fashioned thought experiment. We're going to look at a super simple situation, but from two totally different points of view.
Okay, so here's our setup. Just imagine a single positive charge, just zipping along parallel to a wire. Now, inside that wire, there's a current, which is just a bunch of negative charges, electrons, on the move. But, and this part is absolutely crucial, the wire also has stationary positive charges. They balance everything out perfectly, so the wire itself is completely electrically neutral.
So, let's start with our first viewpoint. We'll call it the lab frame. Pretty simple. This is just us standing still in the lab, watching this whole thing happen. From here, the explanation is pretty textbook. Since the wire is neutral, there's no electric force to push or pull our little charge. But we've got a current, those moving electrons. And as you probably learned in school, a current creates a magnetic field that wraps around the wire. Our test charge is also moving, so it feels that magnetic field, and it gets pushed. Simple enough, right? That's magnetism. Case closed. Or is it?
Okay, now for the fun part. Let's do something a little bit weird. Let's imagine we can shrink down and ride along with our little test charge. We're in its frame of reference now. From our new perspective, we're the ones standing perfectly still. And this is where the paradox hits you. In our new frame, our charge isn't moving. And one of the fundamental rules of physics is that magnetic fields only affect moving charges, so the magnetic force on it should be zero. But we know it gets pushed. We saw it happen from the lab. There is a force. So if it's not magnetism, what in the world is pushing it?
The solution to this beautiful little paradox is one of the coolest ideas in all of physics, and it comes straight from the mind of Albert Einstein and his theory of special relativity.
It all boils down to a seriously strange concept called length contraction. See, relativity tells us that when an object is moving really, really fast relative to you, its length in the direction of its motion actually shrinks. And no, it's not an optical illusion. From your point of view, it is measurably physically shorter. So, let's apply this idea to our wire. From our little charge's perspective, remember, it's the one that's stationary. The entire wire is the thing rushing past. That means both the positive charges and the negative charges inside that wire are moving relative to us, but, and here's the kicker, they're moving at different speeds. This tiny difference in their relative speeds changes everything. Because those two different sets of charges, the positive ones and the negative ones, have different relative speeds, they experience different amounts of that relativistic length contraction. The faster-moving ones, the electrons, get squished together just a little bit more than the positive charges do. Their spacing literally shrinks. And here's the punchline. Because those negative charges are now packed together more densely than the positive charges, the wire is no longer neutral, not from our point of view anyway. All of a sudden, it has a net negative charge. So now we have all the pieces of the puzzle. Let's put them all together for the big reveal. Let's just compare our two views, side by side. In the lab frame, we see a neutral wire, and we explain the push using a magnetic force. But in the traveler's frame, there is no magnetic force. Instead, we see a wire that now has a net negative charge, which creates a simple, everyday electric force that pulls our positive test charge toward it. It's the exact same push. It produces the exact same result. The only thing that changed was our point of view. What one person calls magnetism, another person moving at a different speed experiences as pure electricity.
So magnetism isn't really a separate force of nature. You could say it's a relativistic side effect of the electric force. It's just what the electric force looks like when you see it from a moving perspective. They are two faces of the exact same unified coin, electromagnetism.
And look, this isn't just some clever little thought experiment to bend your brain. This is a cornerstone of modern physics. Scientists have this elegant mathematical framework to describe the single electromagnetic force as it moves and twists through four-dimensional spacetime. So why does all this matter? I mean, it's a cool idea, sure, but this isn't some abstract thing that only applies when you're traveling near the speed of light. It's happening all around you, right now.
Seriously, every single time you use an electric motor, every time a transformer steps down voltage for your phone charger, and yes, every time a magnet holds that piece of paper to your fridge, you are witnessing a direct, real-world consequence of Einstein's special relativity. Without length contraction, none of these things would work, period.
To really put it in perspective, the source material makes this amazing comparison. Realizing your fridge magnet works because of relativity is almost as strange as realizing that gravity works because your head is literally aging faster than your feet due to the warping of spacetime. They're both just fundamental, mind-bending truths about how our universe is put together. And that kind of leaves us with one last big question. Magnetism turned out to be electricity, just seen from a different angle. It makes you wonder, doesn't it? What other fundamental parts of our reality are secretly just something else, waiting for us to find the right point of view to see what they really are?